Let's investigate the cause of Y2K38. This problem occurs when a signed 32-bit integer is used to store Unix time, which is the number of non-leap seconds that have elapsed since the Unix epoch. By convention, the Unix time is set equal to 0 at midnight UTC on Thursday, the 1st of January, 1970. This is the Unix epoch. UTC means Coordinated Universal Time. We want to store the number of seconds after the Unix epoch. One way of doing that is by using an unsigned 32-bit integer. That allows us to store values ranging from 0 up to 1 less than 2 to the power of 32. Observe that 2 to the power of 5 is equivalent to 32. And 2 to the power of 5 minus 1 is equivalent to 31. Let's examine the binary representation of these values if we're storing them in an unsigned 32-bit integer. 0 is represented by 32 zeros. If we count 1 second after the Unix epoch, we can represent that as 31 zeros followed by a 1. If we keep counting and we reach this value, which is 1 less than 2 to the power of 31, we can represent this value as 0 followed by 31 ones. 1 second after this corresponds to 2 to the power of 31 seconds after the Unix epoch. And the binary representation is 1 followed by 31 zeros. And if we keep counting, eventually we'll get to this maximum value, which is 1 less than 2 to the power of 32. And this is represented by 32 ones. So it's all ones over here. Now observe that in this range from 0 up to 1 less than 2 to the power of 31, all of these values begin with a 0. And then the moment we count 1 second above and we reach 2 to the power of 31 seconds after the Unix epoch, we will introduce a 1 as the first bit. So we're using 32 bits in total, and that first bit flips over to 1 over here, and it remains 1 for all of these values after 2 to the power of 31 minus 1. That's an important observation, because we can also interpret that first bit as a sign bit if we use an alternative system. So alternatively, we can use signed 32-bit integers. So if we use a signed 32-bit integer with the 2's complement format, we can take all of these values over here and repurpose them as negative values. So the binary representation, where we have a 1 followed by 31 zeros, we can repurpose that, and we can use that to denote this value over here. So we're actually representing minus 2 to the power of 31 instead of plus 2 to the power of 31. So it's actually 2 to the power of 31 seconds before the Unix epoch. And then we can keep counting from this value over here, and eventually we're going to get to minus 1, which is 1 second before the Unix epoch, and minus 1 can be represented as all ones. So we have 32 ones. So that's the same binary representation we used for this maximum value when we were discussing the unsigned 32-bit integer. So that is a very important observation. That first bit can be used to indicate the sign. If the first bit is 0, then we're dealing with non-negative values. Now the reason I say non-negative and not just positive is because we want to include 0 there. So 0 also begins with 0. And then all of these positive values, they also begin with 0. But then when we go 1 second above and we switch to a 1 at the start, that is interpreted as a negative sign. So all of these negative values, they start with a 1. And keep in mind, we're always dealing with 32 bits in these examples. So if we use a signed 32-bit integer with the 2's complement format, we can store values ranging from minus 2 to the power of 31 up to 1 less than 2 to the power of 31. If we go outside of this range, then we run into a problem which is called an integer overflow. And that is the cause of Y2K38. It happens when we go outside of this range. So the next thing we're going to be doing is converting these values, which are just a number of seconds after the Unix epoch. We're going to convert them into a format where we have the year, the month, the day, and we want to specify the day of the week. And then we also want to have the hour, the minute, and the second. So we want to know precisely when this integer overflow problem will occur. So let's see how to perform this conversion. So we'll consider these two values over here. So here we have 2 to the power of 31 minus 1, and then 2 to the power of 32 minus 1. So we have a side-by-side comparison of how this conversion works. So over here we can see the base 10 representation, and we're dealing with an order of magnitude that is around 10 to the power of 9. So we can use the prefix giga. So this can be read as approximately 2 gigaseconds, and this can be read as approximately 4 gigaseconds. So if we use a signed 32-bit integer, we can store roughly plus or minus 2 gigaseconds. So we can go roughly 2 gigaseconds in the past and 2 gigaseconds in the future. But if we use an unsigned 32-bit integer, then we can just go 4 gigaseconds into the future. But if we use an unsigned integer, we cannot represent values before the Unix epoch. So that's a major limitation. So now that we have the number of seconds represented in base 10, we can express that in this format, where we have the number of days, the number of hours, the number of minutes, and the number of seconds. Now observe that we have this factor of 60. That's because there are 60 seconds in a minute. And then we have a factor of 60 squared. Now we have that additional factor of 60 because there are 60 minutes in an hour. And then over here we have an additional factor of 24 because there are 24 hours in a day. And that explains this 24 times 60 squared. Now over here you can observe the prime factorization of these two values. 60 can be expressed as 2 squared times 3 times 5, and 24 can be expressed as 2 cubed times 3. It's always useful to observe the prime factorizations. So now we can observe that for this value, 2 to the power of 31 minus 1, there are 24,855 days. And there are 3 hours, 14 minutes, and 7 seconds. So we can see the time over here. And in the example below, we can read off 6 hours, 28 minutes, and 15 seconds. So that explains how these times were calculated. But now we need to also convert the days into a format where we have the year, month, and then date. So let's see how we can convert this number of days into the number of years. So first we can observe that there are 68 years. We have 68 times 365. That's the number of days in a year. But we also have to keep in mind that there are leap years. So occasionally we're going to have to add an additional day to each of these years. And it turns out that in this interval over here, from 0 up to 1 less than 2 to the power of 31 seconds, there are actually 17 leap years. So there are 17 occasions where we have to add in an extra day. So that explains this 17. Now, let's move over into this diagram over here. M represents the month number, and that ranges from 1 through to 12. Delta represents the additional number of days we have to add to each month. So every month has a minimum number of 28 days. We can represent 28 as 2 squared times 7. In one group of 365 days, we actually have 13 groups of 28. So we can write this as 28 times 13 plus 1. So there's enough days to make 13 months. But that's not what the Gregorian calendar does. Instead, we redistribute those extra days and we only have 12 months. So we have 12 months and then all of those extra days are redistributed. So for February, which is the second month, there can be either 0 or 1 extra days. So in a non-leap year, February has a delta value of 0. So that means 28 days. But in a leap year, delta becomes 1 for February. And so February will have 29 days in a leap year. So that is taken into account by this number 17 over here. And if we observe month number 4, 6, 9, and 11, these correspond to April, June, September, and November. They all correspond to delta equals 2. So that means that we have 30 days in these 4 months. And the remaining months, they all have delta equals 3. So they have 31 days in total. Now we have to keep track of these values, and specifically this delta value, and we need to keep track of that because we want to know the precise date as well. So if we look at this value over here, we can see 18 is remaining. And 18 is less than 31. So 31 is the number of days in January. So that means we're inside of January. And we have gone 18 days into January. But then we have an additional 3 hours. So we're actually 3 hours into the next day after the 18th day. That puts us into the 19th of January. So here we have the 19th of January, and we also have the year, which is 2038. So that is 68 years after the Unix Epoch. So that is how we got this value over here. So we have to add 68 years, and then we also need an additional 18 full days, and then we have 3 hours into the next day. So that's why this is the 19th. And then we also have an additional 14 minutes and 7 seconds. And if we tick over 1 more second, then that is equivalent to saying that we have gone 2 to the power of 31 seconds after the Unix Epoch. Now, because of the limitations of signed 32-bit integers, this is going to be interpreted as 2 to the power of 31 seconds before the Unix Epoch. So it's actually going to be interpreted as this value up here. And we're actually going to go 68 years backwards before, we're going back in time before the Unix Epoch. And if we go 68 years before the year 1970, that's going to put us at the beginning of the year 1902. And then we also have an additional 18 days. So that means we're going to have to go into the previous year, which is the year 1901. And we're only going to go into December. So December also has 31 days. So that means we're going to start counting from December 31st of 1901. That's going to be the first day. And then the second day is going to be December 30th. And we're going to keep going, and eventually we're going to get to 18 full days from the bottom. And then we're going to go an additional 3 hours back into the next day. So that's going to put us into the 13th of December. So we have the 13th of December, and we have 3 hours backwards into that day. So that means we have to convert the time. We're actually going to have 20 hours, 45 minutes, and 52 seconds. So you can see this time over here, 3 hours, 14 minutes, and 7 seconds, that gets counted by 1 second is added to that, and then that becomes an 8 over here. And now, because we're going backwards in time, we have to subtract that value from 24 hours. So if we add these two values together, we can see 52 and 8, that adds up to 60. So that's a full 60 seconds. We have a full minute. And then over here, 45 and 14, plus that 1 minute gives us 60 minutes. So that's a full hour. And then we have 20 hours and 3 hours, plus that full hour gives us 24 hours. So that's how we get this time over here. And we can see that we're dealing with the year 1901, and over here we have December 13th. And this is the time. So in this interval, and this interval over here, we have 17 leap years in both of these intervals. So that includes years like 1904, 1968, 1972, and 2036. These are all multiples of 4. But we have to be careful because not all years that are multiples of 4 are leap years in the Gregorian calendar. There's actually an exception present over here, and that's why there's only 16 years that are considered leap years in this interval. So we have 2040, that's an example, and then 2104, that's also another example. But the year 2100 is a multiple of 4, but it is a multiple of 100. So that excludes it from being a leap year. Now, there's another year present in this interval up here, and that is the year 2000. The year 2000 is a multiple of 100, but it is also a multiple of 400. So that undoes that other criteria, and it makes it a leap year. So this is how the Gregorian calendar works. So years that are multiples of 4 are treated as leap years, except if they're multiples of 100, except if they're multiples of 400. So if they're multiples of 400, it undoes that condition. So that is why 2000 is a leap year, but 2100 is not a leap year. So this is how the Gregorian calendar works. So that's why we have 17, 17, and then 16 over here. So that is how we get this conversion. And now let's have a look at this bottom conversion over here. We can see there are 49,710 days present here. And we can see also the remaining 6 hours, 28 minutes, and 15 seconds. That explains this time. Now, we also want to consider how many years are present. We can see 136 years. So that means there's 136 years in this interval from 0 up to 1 less than 2 to the power of 32 seconds. And we can also see that there are 33 leap days that we need to consider. So why is it 33? It's because we have 17 in this interval, and then an additional 16 in this interval. And that adds up to 33. And then we have an additional remainder of 31 plus 6. So why am I writing it in these two separate values? 31 is the number of days in January. And then we have an additional 6 days. So we have all of the days in January, and then we're into the next month. We are in February. So we have 6 full days in February, and then we have an additional 6 hours. So that means we're into the 7th day. So we're into the 7th day of February in the year 2106, or 2106. And here you can see the time, here you can see the day. So let's also consider the day of the week. Now, this is an important consideration. So we're starting at a Thursday over here. The Unix Epoch is on a Thursday. We also want to calculate the day of the week for all of these dates. So we can do that with some modular arithmetic. So we need to take this value, which is the number of days, and we need to divide it by 7 and have a look at the remainder. So for this top value, we can see that the remainder is 5. And for this bottom value, we can see the remainder is 3. So this is the mod 7 value. So we take the number of days, we compute mod 7, and that gives us the value that we need to add to this value, Thursday. So Thursday is the 4th day of the week. We can number the days of the week. We can start from Monday, and then Sunday is considered either the 0th day or the 7th day of the week. So you could start counting from 0, you could start counting from Sunday, or you could start counting from 1, which is Monday. So we are at the beginning of Thursday. So we can consider this at midnight Thursday. So that means we're directly in between Wednesday and Thursday. So this is where we're going to start counting. This is where the Unix Epoch is located. And because we did this mod 7 operation, we can work out that this has to be an additional 5 days. We have to go 5 days around this circle. So we start over here, and then we go 1, 2, 3, 4, 5. So that puts us at midnight Tuesday. And then we have an additional 3 hours. So we're actually into Tuesday. So we're no longer at midnight, we have another 3 hours. And that means we're definitely in Tuesday, which is the 2nd day. So that explains why this value is a Tuesday. So on 2038, January 19th, this is a Tuesday. And what if we go back in time? We just need to subtract 5. So we go around the opposite direction. So we again start at the Unix epoch, which is over here midnight Thursday, and then we go back 5. So we go 1, 2, 3, 4, 5, and that puts us in between Saturday and Friday. But then we also have to go back an additional 3 hours. So that means we're going backwards into Friday. So we're 3 hours backwards into Friday. And that puts us over here. So that means that 1901, December 13th, is a Friday. And let's have a look at this final example. We want to add 3 days. That's because this is a different modulo 7 result. So we have 3 days that we need to add. So again, we're starting over here at the Unix epoch, and then we go 1, 2, 3, and that puts us over here between Saturday and Sunday, and then we have an additional 6 hours. So that means we're going into Sunday. And that is why this date is Sunday. So 2106, and then over here, February 7th, that is a Sunday. So that is how to work out the day of the week. So we've put it in a format which is very convenient. So we know the year, we know the month, we know the day, we know the date exactly, and we know the day of the week, and we also know the time. We know exactly what second the issue is going to occur at. So we've seen this little summary over here, which helps us keep track of the months and how many days are in each month by keeping track of this value delta. And we've seen this conversion process over here. And we've also seen this mod 7 process, which helps us work out what day of the week it is. So in conclusion, the Y2K38 problem originates from an integer overflow issue when we reach this value. So if we're using a signed 32-bit integer with the 2's complement format, then we can only store values in this range, from -2 to the 31 to 1 less than 2 to the power of 31. And when we count 1 second above this value, that takes us back over here to this negative value. And that is interpreted as -2 to the power of 31 seconds, and that is actually 2 to the power of 31 seconds before the Unix epoch. So that is the issue, and that is why this is called Y2K38. And there's also a related problem, which will occur in the year 2106. But that only occurs if you use unsigned 32-bit integers to store the Unix time. So this is for unsigned 32-bit integers, and over here this is for signed 32-bit integers, which usually use the 2's complement format.